Okay, good afternoon, everyone. Today, I will be discussing a little bit about some details, which are not details, which are difficult things to treat in the generalized case for the Poisson problem. And the title of this lecture is "The Devil is in the Details." So we will try to understand exactly how boundary conditions are supplied to a partial differential equation in the finite element software DL2. And to do so, I'll start with the Poisson problem that we started with on step number 3. And I'll try to build up on top of this. So the principle that we started from is that we want to solve the Laplacian of u minus Laplacian of u equal f in the domain omega. And we would like to set u equals 0 on the boundary of the domain. In order to do so, we define the trace operator. So the trace operator on the portion of the boundary gamma is an operator that goes from h1 to h1 of omega to h1 half of gamma. And we set the space in which we solve variationally this problem as the h1 0 of omega space, which is defined as the functions which are in L2, whose gradients are in L2, and whose trace on the entire boundary of V are equal to 0. If you do so, multiply with V integrate by parts, the integral by parts will give rise to a part of the integral on the boundary, and the integral on the boundary goes to 0 because of the fact that the trace of V is equal to 0 on the boundary. And so you're left with this variational form that we had here. Okay. Now, let's try to understand what happens if you want to do non-homogeneous Dirichlet boundary conditions. So in the non-homogeneous Dirichlet boundary condition case, the thing is we keep constant coefficients here, so we keep solving the same problem for the moment for the sake of simplicity. The thing is, we can no longer apply Lax-Milgram, for example, and the reason why we can no longer apply Lax-Milgram is because we're looking for a solution that is not 0 on the boundary. But in order to apply the same variational form, we want to have the test function space, the function space in which we formulate the variational formulation, which is the same space as before. So we have V0 as this trace functions, the functions which are in H1 with trace is equal to 0 on the boundary. And we write the weak form as finding u in VG, where VG is actually V0 plus it's an affine space. It's not a vector space, because if you take two objects in VG and you sum them together, you don't end up in the same VG, but it's an affine space with respect to V0, in which you translate with UD, where UD is equal to G on the boundary if you take its trace. Okay. And now we want to make this even more complicated. So we would like to make this as general as possible. So for example, we want to apply this with non-constant coefficients and use mixed boundary conditions. And we would like to have the boundary of the domain split into two parts, which is gamma D and gamma N, where D stands for Dirichlet boundary conditions and N stands for Neumann boundary conditions. And we have two functions which are data. One is GD, so the Dirichlet boundary conditions, and one is GN, which is the Neumann boundary conditions. Now, the same definition that we had before applies, but we only have to use a portion of the boundary that contains the Dirichlet conditions in order to set the test functions. So we set the test functions to be V0 on gamma D, and we call the affine transformation BGD on gamma D. Okay? So we just say these are H1 functions which are 0 on the portion of gamma D of the boundary, and this, sorry, I should have put here a gamma D, which I forgot. And here we have the affine translation of this with respect to any function that is equal to gamma D to GD on the boundary. And now, if you look at the weak form of this, when you integrate by parts, you no longer lose the portion of a grad u dot n that would come out from the integration by parts. However, you can exploit the fact that on the Neumann part of the boundary, that portion is equal to a known function. So you can just replace that part inside the portion of the integration by parts of the boundary and put it on the right-hand side. So if you look at this object on the right-hand side, the entirety of this object is still a function, which is, well, it's still an object, a linear operator on functions V, because it associates to any function V a single number, which is given by this integral. So you can actually look at this as a object in V star, where V in this case is V0 gamma D. So V0 gamma D star is all of this object, not just F, is in V0 gamma D star. So you can always rephrase Neumann boundary conditions as an operator that goes on the right-hand side, integrating on the partition of the boundary. So far, this is not a big issue. The problem here is that you cannot apply Lax-Milgram. So if you look at these two things, Lax-Milgram it would be working if you had the same vector space for the function u and the function v. And of course here, this is not a vector space, it's an affine space, so you cannot do that here. And the way to proceed in particular, the trick to solve this issue, to come out of this impasse, is actually to rewrite the function u as split into two parts. One part which is known, the function that you're using here to translate your solution as an affine translation with respect to V0, and a function which is in fact belonging to V0 gamma D. So UD is arbitrary and gamma D of UD is equal to GD. If you do this, you'll have the same solution, but now you look for a solution which is in V0 gamma D, which is the same space for the test function. So this is a trick that is used very often. And if you look at the formulation of the writing here, you have to make sure that the boundary conditions are correct. So you have to correct on the right-hand side both the terms on the boundary and the terms that comes from the from the product between A grad U0 grad V, and this is A grad UD grad V. And in this particular case, this is known because UD is an arbitrary function that you can choose beforehand, such that GD is equal UD on the boundary of Dirichlet is equal to GD. So this long thing on the right is still an object that is in V0 gamma D star, so we are good to go. Okay. And now the main question comes is, how do you implement the functions space V0 gamma D and the translation VGD gamma D? So how do you actually write these things in terms of the numerical implementation in DL2? So option number one, not implemented in the library, would be to encode this directly in the Dov handler. So you set the Dov handler for this space, V0 gamma D, for example, to be actually smaller. So you don't include the degrees of freedom which are on the boundary, and you force the trace of the functions, every trace of the functions on the boundary gamma D of the test functions, and the basis functions, the global basis functions to be equal to 0. This is complicated to do. The reason why this is complicated to do is because it requires you to do different things according to whether you are on the boundary or whether you are not on the boundary. And these are different things, both in terms of implementation. So you have to change the basis functions that you have when you are with elements on the boundary, or you have to change the way you assemble things when you're close to the boundary. And you have to keep track of the numbering. So you have to eliminate from the degrees of freedom all of those degrees of freedom that used to be in the function space H1 of omega. And those guys over here will not appear anymore here. So this complicates a lot of stuff, including, for example, graphical output. So graphical output is agnostic of the fact whether you have GD in the encoded in the space or 0 encoded in the space. This is just another number, a double number, and you still have to output that as a separate part of the thing. So this is not very practical. So in software, for finite element software, typically one has another two possible options. Option number two, penalty methods of Lagrange multiplier. So you change the way you apply boundary conditions. So you impose the boundary conditions weakly, maybe, or using a Lagrange multiplier. This is possible, and we will see some of this with different types of finite element spaces. For example, if you have a discontinuous finite element space, this is a natural way to proceed. Or option three, which is what we have been doing so far without really noticing it, and we will be discussing about this in great detail today, is the algebraic approach. So we impose things strongly a posteriori, meaning we post-process the linear systems, the solution vectors, and the right-hand side vectors in order to get the correct solution and set to GD the degrees of freedom with super points on gamma D. Whether GD is equal to 0 or D is equal to a non-zero function, this is going to be the same thing in the two particular case. So what's the main idea? So the main idea is you assemble the matrix as if you did not have any boundary conditions whatsoever. So you ignore entirely the fact that some of these i's and some of this j will actually need to be 0. Some of these vi's and some of this vj will need to be set to 0. Once you have done this, you assemble the right-hand side and the matrix in the same way. So the right-hand side here contains also the Neumann part of the boundary. You split the degrees of freedom into constraint degrees of freedom, where C stands for constrained degrees of freedom, which are those that you want to set to something in this particular case, and the unconstrained degrees of freedom, or omega degrees of freedom, the way that I used it here. So I use O for unconstrained because a U was already taken by the actual unknown, so I didn't want to use U, otherwise it would have been very difficult. So I use O for omega and C for constrained on the boundary. And you split the domains in this way. So you have both the right-hand side, which is split, F0 and FC, and the matrix becomes a block matrix, A00, A0C, AC0, ACC. So this numbering is just fictitious. In reality, you do this line by line if you have some degree of freedom which are on the boundary and some which are not, and nothing will change. Okay, so this is just for the sake of simplicity, so to just gather together all the degrees of freedom that are constraints. It can be even scattered all over the places. Okay? It's just to be to show the practical applications of what happens. So what is the idea here? Well, the idea here is that you want to solve the problem A U equal F, and you want to constrain the solution to be equal to something on the boundary. So the thing is, you would like to basically eliminate the row that consists on AC0, ACC. You're no longer interested in solving this equation on those degrees of freedom. You're just interested in setting the identity on the diagonal here and whatever it needs to be on the other side. Of course, however, you want to make sure that the effect of the boundary condition is felt by the rest of the system. So this term over here needs to be taken into account according to what types of boundary conditions you have and according to what boundary conditions you have. So vector tools interpolate boundary values will fill a part of a vector that contains the boundary values. You have already used this in step number 3 and step number 4. You have seen this. You haven't, if you have read the documentation has already explained this to you. But if not, this is now the right moment to actually look at details of what is actually happening here. So this takes all the boundary values. It takes all the support points, the degrees of freedom whose support points belong to the portion of the boundary for which you are asking to interpolate the boundary values. It evaluates the functions that you pass to it at the support points, and it stores the values on the vector which contains, this is actually a map that takes as input the degrees of freedom which is supported on the boundary and the double number that will have to be taken by that degree of freedom. So that GD contains just a list of all the degrees of freedom that you want to have on the boundary. And the way to proceed would be, naturally, to replace the matrix that you had originally with a matrix A00, A0C. So this is still there, exactly as it is. But then, instead of solving something which is the same as above for UD, on UD, you simply replace by the identity times UD equal GD. So this second line over here is enforcing the fact that you want UD to be equal to GD on the boundary. Okay. Now, of course, this would be okay. This you could solve. If you had a non-symmetric matrix, this would be perfectly fine. And you can actually ask the apply boundary values to do this behavior, to behave in this way if you wanted so. However, this doesn't allow you to solve the problems if you have a symmetric matrix, it doesn't allow you to solve the problem using conjugate gradients, because conjugate gradients require the matrix that you apply to be symmetric. So if you want to restore the symmetry of the matrix in some way, you have to get rid of this upper right corner object, which is over here. We can do that by observing that we already know that UD has to be equal to GD. So we can take that A of C times UD, and instead of writing it times UD, you write it times GD and you put it on the right-hand side. So you remove it from here and you put it on the right-hand side. So this is a Gauss elimination step in a certain sense. So you're just basically eliminating all the degrees of freedom that refer to the constraint degrees of freedom. Those are no longer free to do whatever they want to do. So you force them to be equal to GD, and then you take into account the fact that they are equal to GD on the rest of the equation. So this over here will behave similarly in spirit to exactly what we did in the continuous level. So the continuous level, this part over here is like writing minus the divergence of A grad UD on the right-hand side, okay? And now, of course, this would be fantastic if this was well conditioned. Oh, very often this is not well conditioned. So what you need to do, and what you need to make sure, is that you rescale the entries of this matrix in a way that guarantees the correct scaling with respect to these two parts of the matrices. So here you put an alpha that takes into account what you had originally in this part of the matrix and replace that by what was originally in that part of the matrix. Typically, either the maximum value on the row that you have eliminated or the sum of the absolute values on the row that you've eliminated. So some L1 norm of the row or some L1 norm of the column. And this is done in order to maintain the good conditioning of the global system. Of course, if you scale this by alpha, you have to scale also the right-hand side here by alpha. And as you see, the solution of this problem is done by simply post-processing the matrix that you've assembled, ignoring the fact that some of the degrees of freedom are constrained to be something on the boundary. And this is done by two calls. One is vector tools interpolate boundary values, and the other one is matrix tools apply boundary values. So matrix tools apply boundary values modifies three objects. So the first object it modifies is the matrix, the second is the solution, and the third is the right-hand side. So in the solution here, you can either put UD, which means you don't change the solution, or you can already put GD because you know that this is going to be equal to GD. So usually I forgot to write that here, this is actually replaced by U0 GD, not U0 UD, sorry. So this should be GD. So what the apply boundary values does, it modifies the right-hand side, it modifies the solution vector, and it modifies the matrix so that this is okay. Okay, so from the practical point of view, this is the way that boundary conditions are applied. And this is, in some sense, it's a special case of what the class, which is called AffineConstraints, does in the library, in the DL2 library. So this is the preferred way to use, is to use AffineConstraints instead of using these two functions over here. And now I'll explain briefly why this is the case. So in the general case, the constrained offs, instead of being constrained to be something, like in this particular case here, if you had C, which is equal to 0, in this case, if you want to constrain the ith off to be equal to bi, here I'm using this as a set of indices. So NC are all the indices which are constraints, and N are all the indices in your degrees of freedom. You can always write if you have constraints, you can set one of the constraints to be a multiple of a linear combination of all the other unconstrained degrees of freedoms plus an affine transformations, and that's why it's called affine constraints. So this is a general type of constraints. We will see where this is used in a few slides. But if you have these types of constraints and not just xi equal to b, then you have to do a little bit more steps in order to provide a good solution for your system. So the idea here is that you can perform an algebraic solution where you impose these types of constraints by doing this in 3 steps. So you first condense, so you perform kind of the same thing that we did before, but taking into account the fact that you also have a matrix here that multiplies your unconstrained, the unconstrained degrees of freedom to make them equal to the constraints degrees of freedom. You solve the system, and then you distribute this, which is only needed, of course, if G is different from 0. Okay, so let me show you how this is done. So given the two matrices that are assembled as if you didn't have anything, and the constraints that can be written as, you write UC as a matrix times U0, UO plus B, you take into account in the lines that take this, in these lines over here, you take into account the constraints. So instead of writing AOO plus AOC UC, you replace this UC by C times U0 plus B, and you obtain a matrix on the top left corner, which is no longer AOO, but it's AOO plus AOC times C. And you take something which is given by the affine part here, which is the non-homogeneity part of the constraints, and you put this on the right-hand side. So basically what happens here, you replace this by a matrix in which you solve in the first line what you would have had with the constraints known, if you know exactly what the constraints are. So you just replace the top left part of the matrix by AOO plus AOC. And as we did before, this part will go on the right-hand side, so it has FO minus AOC times B. This is the same thing as before with B that replaces GD. It's identical. And in addition, you have this part here when C is different from 0. So you have the same thing that we did before. And now the idea here is that you solve for F tilde, which is F0 of O FC. You replace that with FO minus AO BC and alpha B. And after you have solved the problem in this system, you're still not finished because U constraint is not yet C U0 plus B because you eliminated it from the matrix. So in what you obtain if you solve the system in this way is that UC is equal to B in particular. So you want to make sure that from U0 times B, U0 UOB, you go to UO and C times U0 plus B. So you have to distribute the constraints that you have computed, that you have coming from the solution UO, which you didn't have before, to the constraint variable. And this is called distribute constraints. And this is exactly how this is done in the library. So why is this useful? Well, this is useful in particular for something which is extremely important for the Dirichlet library or for libraries that do not want to deal with very complicated uniform refinements. So in other words, this is very useful when you have, for example, hanging node constraints. Let's take a look at what happens with hanging node constraints. So hanging nodes are a particular ways to provide local refinement of cells. So assuming you start from a square, which is the one that you see on the background, and you refine globally once. And then you figure out that your solution actually is singular on the top and the bottom left corner. So you want to have more of refinement on the bottom left corner with respect to the rest of the domain. So what you do, you add local cells. And since you don't want to refine all of the others, because this is not necessary in these parts for reasons that will be obvious to you when we do a posteriori error estimation, when you want to only refine these parts over here, you have these guys over here, which nodes with these vertices that do not correspond to vertices on the other side. So these nodes here are usually referred to hanging nodes, in the sense that they hang on one part of the face with respect to the other part of the face. So when you have hanging nodes and you try to apply the definition, for example, of a Q1 finite element space, the Q1 finite element space, questions? Okay, so Q1 finite element space associates to vertices to every vertex of your triangulation. So including those vertices which are hanging on a face, it associates a degree of freedom that is a basis function. So if you look at the guys over here, if you look at 0, for example, this is the first degree of freedom that we have on this level, and 0 of x is actually a function which is equal to 1 here and is 0 on all other support points by definition. So by the definition of the support points and the basis functions that we have. If you construct it in this way, this function is no longer continuous in the sense that this degree of freedom here is set to 0 for this particular basis functions. And in the support points that we have, if you compute this in the standard way, so you take n capital I, so n I on top and 0, x has to be equal to 0 for all I on top except for 0, then this is what you would get when you plot this type of basis function here, okay? Of course, this is not the case just for n0, but also for n2. So if you look at this n2 basis function here, you would have a function that is equal to 1 here, 0, 0, and 0 there. So actually, I think I didn't write them with the correct order with respect to here. Sorry about that. I would have to correct this at some point. So I'll correct this. Sorry. But this is the same. It's different. So it's this degree of freedom here in a certain sense. So you're setting this equal to 1. Yes, it's the correct one. It's just rotated. Sorry, it's rotated in the wrong way. So I should have put this here on the bottom right. Okay, so n2 is this part in the center. So it's a function which is 1 here, 0, 0, 0, 0, 0, 0 here, 0 here, and 0 here. So it's bilinear on each one of the elements, and it's 1 just on this vertex. And of course, you can do the same for the number 12, which is this guy over here. So I'm just looking at this 3 basis functions, 2, 12, and 0, or 0, 12, and 2. which is the 0, 2, and 12. And of course, all of these are discontinuous. The 12 is the one that is the most hanging in a certain sense, because it's the one that is 1, and it's free to float and to go up and down as it wishes, and it will blow up when you look at it in this way. Now, of course, the discontinuity of these edges are in across the edges 0, 12, 2, and 2, 13, 4. And you have two possibilities. You either use standard shape functions that require continuity for the linear combinations. These are the guys. And you can make them continuous by enforcing those degrees of freedom that you have here. So the ones, number 12 and number 13, not to be actually free to do something, not to be free to do whatever they want, but just to be a linear combination of the degree of freedom, which is number 2 here, and number 4, or number 2 and number 0. So if you look at this in this way, then you can rewrite this as a continuous basis function, as you see this in the picture, by enforcing this type of constraints. So I force U12 to be a half of U0 plus a half of U2. So it's exactly in between U0 and U2. And U13 instead is in between U2 and U4, between U2, which is the one here, and U4, which is the one here, if I'm looking at this rotated. Okay? Questions so far? Okay, so in this way, what happens, this is exactly the form that we had before. In the general form, you have these types of equations. You define the subsets of all the DOFs to be the one that is constrained, and you solve for a different type of shape functions. So you don't solve for the original shape functions. You solve for n tilde shape functions, which is a linear combinations of the previous shape functions. And so in a certain sense, the space of the degrees of freedom that you're currently using is not the original space, but it's a space which is the one without the constraints, in which you express the basis functions with the correct condensations, with the correct linear combinations between them. Okay, so this is a little bit complicated to grasp at the first sight, but the idea is simply that instead of using the basis functions as if they were defined by using just one single super points, you basically use them. You basically provide basis functions which are linear combinations of existing basis functions. So the idea, you can assemble the system matrix by either assembling directly this. So you take this into account when you assemble the matrix, which is complicated, or you do exactly as we did before, is you assemble the matrix exactly in the same way, identically to what we did when you didn't have angular constraints, when you didn't have boundary conditions, and then you condense this separately, as we did with the examples that we did before. So this is the beauty. You can do this everywhere, same thing in every cell, and then you do everything as if you didn't know what was happening to the constraints, and then you apply the constraints afterwards. So the idea is you build the matrix with all the DOFs as if there were no constraints, and then you modify those to get the correct ones. So the ones that would give you conformity in C0 in a certain sense, and then you solve for this one. And once you have solved for this one, you fill the constraint components of U to be the correct ones in order to have the correct visualization. So this is an approach that works very well, but it has a few problems and a few drawbacks. So this approach requires you to modify the matrix after you have created. So this is one possibility, and it's exactly what the matrix tools apply boundary values does. Okay, so the matrix tool apply boundary values does this, and it's very disadvantageous for higher order and HP finite element methods, because, or when you have parallel processes, because you have to communicate to all of the degrees of freedom that are constrained exactly what is happening, and you may not have access to those guys after you've assembled the matrix. Okay, and of course the two matrices have different sparsity patterns, so you have to take that into account when you construct things. The approach here looks in the following way. So here we have the 12 degrees of freedom and the 13th degree of freedom, which are actually constrained, and the constraint matrix looks like this. So I'm just showing your U0, U2, U4 as a little constraint matrix with respect to the local matrices that you have here. So U12 is equal to 1/2 U0 plus 1/2 U2, and U13 is equal to 1/2 U2 plus 1/2 U4, exactly what you see here. So that the 13 is between 2 and 4, and if you want continuity, its value has to be equal to exactly the average of 2 and 4. And the same thing is valid between 2 and 0. You have average to be equal in this case. So you start with the matrix which is uncondensed. And if you have the matrix which is uncondensed, this matrix, so the constraint matrix will be written exactly in the same way that you see here. So 12 has a constraint with vector with the index number 0 with the value which is 0.5, which is this guy over here. 12 also is constrained with respect to degree of freedom number 2 with the constant which is 0.5, and so on and so forth. So this is a very compact way to write a very, very sparse matrix that only contains very few non-zero entries. And that's why it has a separate class to tap this, and we don't use a sparsity matrix for that, sparse matrix for that. In the condensed matrix, what you will see is that these guys over here that are now in blue, so just take a look at the line number 3, which is U2, this will change. And this will change because what I'm doing is I am basically eliminating from the degrees of freedom on the bottom right, whatever was the ACC matrix, and I'm trying to keep the same thing that we had in terms of scaling, but now I've eliminated the part on the right-hand side that you see here. And if you look at the bottom part of the matrix and at top right part of the matrix, this has become entirely 0. Okay, so this is a good approach. It does exactly what we saw before. So on the left part, you modify and you write A minus A plus AC. Well, this matrix over here times the constraint. So you will see that if you look at the numbers that appear over there, I'm taking this 1.767 and I'm multiplying this number over here with 0.5 and adding the two things, and you get exactly this number over here, which is 8.33 10 to the minus 2. I'll let the rest to you, but this is exactly what is happening. So what we wrote at the beginning. So you modify the top left part of the matrix, eliminate the two sides, and set an identity with a scaling on the bottom right. And this is the approach that modifies the matrix afterwards. Approach number 2. You build the local matrices as if there were no constraints. And during the assembly procedure, so when you copy the local matrix to the global matrix, you take into account of the constraints and of the possibly non-affine constraints. If you do that, when you transfer KK and FK from the element K to the global one, this can be done by taking into account the constraints right away. So you solve the final matrix entirely, and you still have to distribute at the end, but the result is that the global matrix will not contain anything on the condensed version if you do this while you assemble the system. Okay, and so this is exactly the approach that is used by step number 6, and the class that is used for this is called AffineConstraints. So the interesting part about the library is that this class over here allows you to assemble the things by just having say around 10 more lines of codes that you write in your programs. And it allows you to keep into account of affine constraints for boundary conditions and for all type of HP constraints. So for all type of constraints between different types of finite elements from the left and from the right. And if you look at the actual implementation, the implementation of this is about a few thousand lines of codes. And from the perspective of the user, it's very simple to use. And the reason why it's very simple is because all the heavy lifting is done in the background. And it's done by taking into account how to match all the various degrees of freedom according to the degree, how to match the possibilities of having degrees of freedom which are actually not doubled on the two sides. So for example, the support points on a face, if you have, for example, on one face you have Q1 and on the other face you have Q2, you have to take into account of how to constrain the degrees of freedom in such a way that there's continuity between the two, and so on and so forth. Okay, so if you look at this, the hanging node constraints are created using the function called make hanging node constraints. And this is done in step number 6. You will see this and we will try to apply that. And you can interpolate boundary values that instead of taking a map as an input term, it takes a constraint as an input terms. And this will add the constraints of the boundary conditions on there. So this will allow you to use the affine constraints for the boundary conditions as well. And then when you construct the sparsity pattern, we can either decide to keep the constraint stuff or to eliminate the constraint stuff from the parts of the matrix where this is not needed. And this saves a little bit of space. If you don't have many constraints, this is not really necessary most of the times. If you have a lot of constraints, or if you have a lot of, for example, HP functions in 3D, then this may make sense. You may save a few sets of megabytes of data for that. And then you sort, rearrange, and optimize by closing the constraints. These are added. So this object is not really a sparse matrix. It's something which is much more efficient to be constructed with respect to a sparse matrix. And it's compressed in such a way that the access to this guy is very fast. So the creation is done in a way, and then the access is done after you have optimized everything internally in order to avoid, for example, all the cache misses that are possible in these types of problems. Okay, so how do we go forward? How do you assemble things? Well, you basically do the same thing as you were doing before with local matrix and local vectors, but then instead of copying manually those guys from the local matrix to the global matrix, or from local vector to the global vector, you distribute those by distributing local to global, taking into account of the constraints using the function called distribute local to global in the constraint matrix. And you distribute the cell matrix, the cell right-hand side, using local loaf indices to the system matrix and system right-hand side. This is equivalent to writing the loops that we had in step number 6 and step number 3 and step number 4. And now, once you have solved, if you want to have all the constrained degrees of freedom to the correct values, you call distribute at the end of this. And notice that if you don't have C, so if C is equal to 0, then this may not be necessary. If you have a C which is different from 0, then this is necessary, because during the solution process, we ignore what happens to the diagonal that contains all of the constrained degrees of freedom. Those are no longer degrees of freedom, they are just constraints. And we construct them a posteriori, knowing the exact values of the solution. So for example, if this is constrained, then we only need U1 and U2. You need to solve for U1 and U2 in a correct way, and then you replace back into U8 what it should be, okay? Of course, you can merge constraints. You can have sets of constraints that don't overlap. Typically, these are not overwritten. If you have loops in the constraints, you have to be careful, because you cannot do that. So if you set U1 to be equal to U2, U2 to be equal to U3, and U3 equal to U1, you'll get an error. Of course, this is not possible. But you can have situations in which, for example, U1 is equal to U2, U2 is equal to U3, and U3 is equal to U4. And if you apply the constraints dot close at the end, you only have one of these guys equal to U4. All of those will be equal to U4, and all of the others will be eliminated from this count, right? So you will not have these loops in here. So in other words, the matrix is constructed, the constraint matrix, the affine constraints are assembled in a very fast and efficient way at the end of the problem. Okay, so let me stop and end the share over here, and let me start with the exercises that I've assigned you. You should have, let me copy this again, the link in the chat to accept the assignment for this week. And now let's go to the actual assignment and see how this actually works. Okay, laboratory number 5. You should see my entire screen. I'm here, and let me just remove this on the right-hand side so that it's not in many other things. Questions so far? No questions. Okay, very good. That means I've been very clear. So let me take the laboratory number 5 description, and let's try to analyze what's written here. So laboratory number 5, I am basically generalizing what we did for the Poisson problem before, using Neumann boundary conditions and using affine constraints instead of the vector tools apply boundary values that we had before, okay? And the affine constraints that we have here is the workhorse that will be used also for hanging node constraints. So at the end of this part, we have also local pre-refinement grid size expression. And so far, I'm not doing any a posteriori error estimation in this exercise. I'm assuming that you give me a function that tells me how big has the cell has to be in order for me to decide whether we need to do refinements or not. So this is a good way to introduce some local refinement that you can control with some parameters, so you can play around with this a little bit. And in order to do this, I have given you access to the code that I've used for the solution of the previous exercises. So of course, if you want to cheat in a certain sense, you can copy what's written here in laboratory number 5 to laboratory number 4, and everything will work out of the box in laboratory number 4. But of course, you will not learn anything in this way. So I'm doing this so that you have something to compare with and something to work with and to develop on top of. And I'm assuming that you'll work on this from now to next week. And if you need time and if you need more, I will open up a students meeting again, maybe before next week, either on this Friday or maybe on Monday, so that you can actually ask me all the questions that you may have. Okay, so let me show you a couple of changes that I did to the code to make it a little bit more similar to what really happens in real life. So if you recall, I told you some time ago that the tester that we created was not templated. So the tester was constructed in a way that you can actually, you had to repeatedly call this for tester 1D, tester 2D, tester 3D if you wanted to test different types of dimensions. Now I've changed that, and you'll see this into the file PoissonTester.h. So the PoissonTester.h, let me close all of this for the moment, and let me just open that PoissonTester.h. So the PoissonTester.h now contains a Poisson tester object, which is templated with respect to a class. And this is a little bit strange, and it's due to the fact that the Google test framework does not allow you to instantiate a tester class for integer values. So it allows you only to instantiate the classes, instantiate template classes with actual classes themselves. So C++11 allows you to turn around this, to work around this little thing by using as an integral class the so-called std, let me call it here, it's std integral constant. And this integral constant is basically a class for every integer that you specify here. And you can access as a context the guide that is written here. If you're not understanding what I'm writing here, this is what I'm saying here. Don't worry. It's only a trick that is required for Google Test to actually be able to run on 3 different types. And the 3 types that I want to run this Google Test on are these 3 integral classes. From these 3 integral classes, I can extract a single number, which is 1, 2, or 3, which is known at compile time. And with that number, what I'm going to do is I am going to create my tester as a public interface with respect to the Poisson class with the dim value replaced by integral column value. So the std integral value replaces that object with 1, 2, or 3 in this case, which is the Poisson class over here. Sorry, the Poisson tester, which is over here, this guy over here. So I'm saying I want to use 1, 2, and 3 over here. And the Poisson test types are passed to the typed test case Poisson tester. So whenever you run this Poisson tester object over here, it will be run for dimension 1, 2, and 3. Okay. And instead here, I'm showing you how to run this just for 2-dimensional test cases. So for example, if you construct an example that you know it's only going to work for 2D, you don't need to call the Poisson tester. You can call the Poisson 2D tester. And this is exactly the same that you did before. That's a test fixture, it's called. So it's calling the Poisson tester initialized with just the integral constant equal to 2. And in this particular case, instead for the type test, what is happening is calling these guys for all of these types. So for 1, 2, and 3. If you run this, for example, you go to build and run the G-test, you'll see that this is run 4 times. 3 times with the Poisson tester with dimension 1, 2, and 3, and once for the Poisson 2D test. Okay, and you'll see this in the names as 0 make grid, 1 make grid, and 2 make grid. And here it tells you exactly what it's doing. So a type parameter is an integral constant 3, and here I'm outputting the parameter value of type param, which is the guy that is over there, and the type param value for me is dim, for which I instantiate the things. So this was something that I didn't want to do on the last lecture, but now I did it for you, and you have it here so that you can actually run all the tests in a simpler and more convenient way. So let's go to the Poisson.cc, and let's start by looking at what I'm asking to you for this guy over here. Okay, so let's look at the other thing. So the first thing is Neumann boundary conditions. So for the Neumann boundary conditions, I would like to add, of course, Neumann boundary conditions expressions, and then split the boundary IDs into Dirichlet and Neumann boundary IDs. So let's do this. You will see this in the same way that we did before. And then the most difficult part is going to be the last point, which is this guy over here, local for refinement grid size expression, but not too difficult, but we will take a look at it in great details. So let's start with the Neumann boundary conditions. And let's go to the, in part here, I should have a Poisson.h file opened. Okay, so I had a function parser with boundary condition, and I'll add a function parser with Neumann boundary condition. And actually, before doing that, let me take this boundary conditions and let me replace the boundary condition with Dirichlet boundary conditions so that we are sure that I replace all of the occurrences of boundary conditions with Dirichlet boundary condition. Okay. Okay, and now I can add Neumann boundary condition. That's the actual function, and here I have the Neumann boundary condition expression. Okay, this is the first part, and here, if in the boundary condition expression, I duplicate this and I'll rename this as Dirichlet boundary condition expression and Neumann boundary condition expression. And the second one, of course, has to refer to the Neumann boundary condition expression. Okay. After having done this, the parameter files will contain two objects, Dirichlet and Neumann boundary conditions. And I want to make sure that when I set up the system, the Dirichlet boundary condition and the Neumann boundary conditions are initialized correctly. So this is Neumann boundary conditions initialized with the Neumann boundary conditions expression. If there are questions, please stop me right away and ask right away. And if I'm going too fast, please stop me. Okay. So this is the initial part of the exercise. And now the difficult part of the exercise is to actually make this into the assembly routine. So make sure that in the assembly routine, we do the right thing. So how do we do this? Let's take a look, first of all, at which boundary IDs we want to apply this to. Okay. So for the moment, we didn't specify any boundary IDs for our boundary conditions. So all the boundary conditions were always applied on the Dirichlet IDs, on the boundary IDs equal to 0 in the particular case. So here now, I am trying to create a new member objects that will tell me what are the Dirichlet IDs on which I want to assemble boundary conditions. And by default, I'll take this to be the set of 0 Dirichlet IDs. And instead, Neumann IDs, I don't set anything. So this is empty by default. And of course, I want to make sure also that these are written here. So after writing the expression of these two guys, I want to make sure I also have Dirichlet boundary IDs and Neumann boundary IDs. And this is Dirichlet IDs here and Neumann IDs here. And just to make sure that I'm doing the correct Dirichlet boundary IDs, Neumann boundary IDs, Neumann boundary condition expression, Neumann boundary condition expression. Okay. Okay. So these three things alone don't do anything, of course, but I now have the parameters that I can play with. Okay. So let's start and let's go to where we have the interpolate boundary values. And instead of calling interpolate boundary values with this, in this way, what one can do is one can do for const auto and actually const auto and ID into the Dirichlet IDs. What I do is I interpolate the boundary values with the ID instead of doing that just for one. And if I do this loop, what's going to happen is that this loop is going to fill boundary values with the Dirichlet boundary condition function evaluated on the super points corresponding to the boundary portion of the domain with boundary ID set to ID. Okay, so far nothing has changed because by default I set equal to 0. So this should give me the exact same result as before. But now I'm allowed to change that. So I can change, for example, I can say that I want to colorize the boundary conditions and set 0, 1, 2, and 3. And I can set, for example, Neumann IDs and 0 and 1 and Dirichlet IDs and 2 and 3, for example. Okay. So this is the reason why I'm doing this exercise. So for the Dirichlet IDs, nothing has changed. And now the difficult part becomes the actual Neumann boundary conditions. So the Neumann boundary conditions requires me to evaluate finite element spaces on faces of the boundary, on faces of the cells, not just on the cells. So I will need a similar object that I've been using here, which is called FE values. But instead of having FE values, I will need to have an object which is called FE face values, which is used exactly for the evaluation of finite element functions on the faces. Okay, so I will have Q Gauss of dimension b-1 for faces. This is phase quadrature formula, and the FE face values will be, I will call this as FE face values. I use exactly the same thing as initialization, and then we'll see what we need after that. So this is going to be FE, and then phase quadrature formula, and I just need to use values. I will not need the gradients, and I will need the quadrature points and the Jacobians of the gradients. Okay. And the reason why I need this is because I need to integrate on the boundary condition. Also, I need to integrate on the, when I am assembling the right-hand side, I need to make sure that I add to the right-hand side term also the integral on the faces that are on the boundary with the correct boundary IDs, the values of the shape functions times the function evaluated at the quadrature point. Okay, the function that I just added at the quadrature point. Okay, so how do we do this? We are looping for all the cells. So this is on the active cell iterators over here. And then I'm getting the DOF indices here to do the assembly around the end of the loop. Before I do the assembly, I have to add on the right-hand side, I have to add the integral of the faces that are on the correct boundary condition. And in order for that to work, I have to make sure at the end of this loop that I check if the cell is at boundary Okay, and cell. Oh, sorry. If the cell is at boundary, what I need to do is I need to loop over all cells. Over all faces, sorry. Const auto face cell face indices. I don't remember whether this is actually been introduced. I'm using now 9.2 in honor of Irina so that we don't need to do this for 9.3. So for cell, I don't remember whether this is implemented in 9.2, maybe not. If it's not implemented, what one does here is construct this by looping over all faces, fs f smaller than of course nice. This is nicer. The one that is on top is nicer, and this is an approach which is the old approach that is used for this type of things. So if the cell is at the boundary, what we do is we loop over all faces and we check if the cell face F, and then we ask for the boundary ID. And if this object is into the Neumann IDs, find that. And this is different from Neumann IDs end. That means I have the boundary ID of this face on the Neumann IDs. If this is the case, then what I do is I need to call FE face values, reimit cell, and these face values, if you look at this guy, takes two objects. One is the cell and the other one is the face. So it's either the face or the face number. Okay, so I can call this with the face number or with the face iterator. Okay, and as soon as I have initialized this, I can access values of this guy and I can access correction points of these guys. Okay, so let's go here and I'll copy this loop for this Q index FE phase values. Correction point indices. Then I loop for the unsigned int FE phase values DOF indices. And now what I want to do is add to the right-hand side I what? I want to add the FE phase values, shape value, I at Q index, multiplied with the Neumann boundary condition function, evaluated at the FE phase values, quadrature point Q index, times the FE phase values, Jacobian times weight at the Q index. Okay, so let's try to understand what is happening here. What I'm doing here is after I've assembled the right-hand side with the false-in term, there was this guy over here, what I do, if I check if the cell is at the boundary. If it is at the boundary, I loop over all faces and I ask whether the face boundary ID is equal to something which is contained in the Neumann IDs that I'm trying to integrate for. Okay? If that's the case, then when I have this, the FE phase values is reinitialized with the current cell and the current phase, which means after this is done, I will know the location, I will know the values of the quadrature points, the values of the shift functions of the quadrature points and the J times W of the quadrature points of the finite element spaces computed on the given phase. Okay, so this uses exactly the same type of knowledge that has been used here, but on the faces instead of being on the boundary. Okay, once I do this, I will do the same type of assembly that we have here. So I assemble by getting the DOF indices, the local DOF indices, and looping over all indices to add to the system matrix and to the system right-hand side. Okay, so here I take into account of the Neumann boundary conditions, and here I take into account of all the Dirichlet boundary conditions. So let's try to build. I will have a lot of errors, of course, and then we will try to debug what errors we get. Okay. So braces around scalar initializer. This should be able to fix that. This depends on the compiler that you use. If you use a certain types of compilers, this will complain about the type of initialization that we have here. Neumann boundary conditions expression. Use of undeclared identifier. Let's see. I'm pretty sure that there was just a simple misspelling. Probably. Boundary conditions expression. Did you mean, okay, so this looks exactly identical to me.
Like 100, yeah, here there is a misplace of U and E at the beginning. Neumann, not Neumann.
Ah, I see. Neumann, right? Okay, thanks. So these are the type of things that if you don't see it right away, it's basically impossible to see. Yeah, to me, you said yes. Did you mean yes? Of course I meant yes. Okay, so if this is the only error, I'm very surprised, but we will see. All right. So this seems to have worked out of the box. Usually this is even worse news because then the bads are much more difficult to find. If everything works out of the box, beware, it's always not the case. So let's try this problem at the moment with the new parameter file, and we call this Neumann.prm. It will complain that we don't have the file Neumann.prm, and we'll create it for you. So Neumann.prm is now this function over here, this object over here, contains the error table, and then Dirichlet boundary conditions expressions is 0, Dirichlet boundary IDs is 0, and then I have Neumann boundary IDs, which is an empty set, and Neumann boundary conditions expression, which is 0. Now, to check whether this is actually working as we expect, one thing that we could do is, of course, we can run this once, and it doesn't seem to be giving anything particularly difficult. So let's say that we do, for example, 6 global refinements, just one cycle, and we open the solution and see how it looks like. And then we try to see whether we can get something more interesting with respect to the usual Laplacian on a square, which is something that we always get as a test case. Okay, so this is surface with edges, nothing really strange, nothing really particular about this. We warp this by scalar, and we make the solution 3-dimensional and rescale everything so that things look actually nice. So we make this like that. Surface with edges, make it 2. And now we try to change a little bit things. So for example, here, the grid generator argument, the last parameter here, it's usually called the colorize of the hypercube. So if I set the colorize to hypercube to true, what happens here is that it will set the boundary conditions to be 0, 1, 2, and 3. And if I set 0, 1, 2, and 3, what happens is that it's going to use homogeneous Neumann boundary conditions for all the cases in which I don't specify anything. And it will use the Neumann boundary condition expression that I have here, which is 0, for all the cases in which I specified here. No cases so far. So this has never been used so far. And so I want to try a couple of things. So let's try to start with 0 boundary conditions first on one side and Neumann boundary conditions homogeneous on the other 3 sides. And if you reload this, you should see a different type of solution, hopefully, but not. For some reason, it did not. And of course, it's not Poisson, but it's Poisson-Neumann. Otherwise, I'm not solving with the correct boundary condition. Okay, right. So let me rescale this to be 1. Otherwise, you don't see what is happening. And voila. So this is Dirichlet boundary conditions on face with the number 0, and homogeneous Neumann boundary conditions on all the other faces. So if you look at the normal derivative across the other faces, you'd see a flat solution on the 2 sides. And on the 3rd side, you should see a flat condition here. So if you look at this from the side and set the visualization to 2-dimensional, so if you set this to 2D, you don't see anything. If you set this to the so this is 3D. If you look at this from this side, the exact solution here should be half of a parabola. So this is exactly the type of solution that I'm expecting, because I have as Poisson term expression, I have 1, and I have 0 boundary conditions on the right, on the Neumann, 0 Neumann boundary condition on the right, 0 Neumann boundary condition on top, and 0 Neumann boundary condition on the bottom. And on the left, I have Dirichlet boundary condition. So I expect this exactly to be in this way. And now I know that the numbering in DL2 is lexicographic numbering. So that means this is face number 0, opposite face is number 1, bottom face is number 2, top face is number 3. This is in the documentation of the grid generator hypercube cell. It will tell you what's the numbering of the faces. I know this one by heart. And if you now want to change things and actually see things in action, I would like to see, for example, that if I put 1 as a Neumann Dirichlet condition on the right, I should see something which is inclinated with direction 1, and this should be a parabola with the direction 1 on the other side. Okay, so let's start to take a look at what happens in this particular case. So in Neumann boundary condition expression, I put 1, and now I put a 1 also as the Neumann boundary IDs on the right-hand side, and I try to solve this again and see what happens. Now, let's see. And I have, okay, so now the inclination here is no longer 0. The inclination is u grad a dot grad u is equal to 1. And it tells you that the inclination is positive inclination towards the outside. Okay. Now, if I want to see something a little bit more interesting, I'll put, instead of condition expression 1, I put -1. And I run this again. And you will see something which is a little bit more interesting, but not too much more interesting. So this is still a parabola, but then now it looks like the left part is Neumann, is Dirichlet, and the right part is Neumann with inclination -1. Okay, so you should play around with this a little bit and try to figure out how things are going. And of course, now that we have this, we can make this, for example, a Neumann boundary condition expression. We can set this to be the sine of pi times y. So this changes on the y direction. So this is a good example, for example, on how to make things Nice. And the problem constants, I want to set pi to be 3.14, my personal approximation of pi. And now if you reload this, you will see a boundary condition here, which is a little bit more intricate with respect to what we had before. Okay, so you have different type of inclinations on the right and here. Okay, so this tool allow you to play a little bit with how things work. Okay, now let's go to the second part of the exercises, and let's start. And this is something that I wish I had done early in my career, much more often. So let's do things the proper way. So to do things proper way, it's important that we understand exactly what is happening. So let me tell you what I mean by understand exactly what is happening. I would like to create a couple of tests and verify that everything that we have actually works. So this is what I've asked you to do here. So to create a function that passes parameters from a string to be used in the testing infrastructure. And now I will test these functions that we just created. You just measure this, you run this, you see what is the correct output, and then you copy the relevant parameter files into the testing infrastructure, and you make sure that you get the result that you expect. Okay. If this is the case, then you can play around with your code and make sure that everything actually does the correct thing for you. So let's try to understand exactly how to do this. And the way to do this for me is to create in the Poisson.h a new function, which should be called initialized with a string file name. I will create here void pass parameters. And I will call this const as to the string and parameters. And now in the Poisson.cc, I do in the same fashion that I did here is pass parameters that I have here. Instead of going parameter acceptor initialize file name, what I do is in the parameter acceptor class, there are functions that allow you to pass the parameter files and pass all parameters or declare all parameters. Okay, so after you've constructed this class, the parameter acceptor PRM contains a parameter handler that you can use for your things, and the parameter handler class in DL2 has an option that allows you to pass parameters directly from a string. And this is what we're going to use. So there should be parse input from string, which is this guy here. Okay, and so we are going to call this guy. So in the class parameter acceptor pass input from string, and instead of calling it file name here, we had to call it parameters. We parse it from the string, and then we are going to call parameter acceptor parse all parameters. So this parameter acceptor class in DL2 has a function which is parse all parameters, which by default takes the parameter acceptor PRM as an input, that will fill the parameter with using this parameter objects here, will fill all the values that you have specified using parameters after you have set those into the parameter handler here. Okay, so with this function, it should be possible to go to the tester, Poisson tester.cc that we have here, and say, for example, Poisson 2D tester. So let's make this only a 2D test. Okay, so I should be able to do, for example, this parse parameters, and then I pass as a parameter a string that contains something which is nice here. Let's eliminate all the things that we don't need. And let's copy this for the moment. So I never remember how to do this. Row string C++. Row string term. I don't want to escape all the \n. And it's L. If I think. Nope. So the equivalent of 3 brackets for C++, I don't remember. There should be one, right? Nope. Never mind. I will use this in the correct manner. Okay. So let me try to show you what I want to do here. So what I would like to do here is the following. So test linear, okay? And I would like to make sure that the output that I get with the test linear is a function which is actually 0 when I solve the linear function on using just boundary condition, just Dirichlet boundary condition. Okay. So in order for this to be possible, what I need to do is the following. I would like to create this file here as a string. And then I would like to change the various things that I need to have as an input file as an input string just to the function that I've created here with the pass parameters object. Okay. So if I look at the pass parameters object that is written over there, what I would like to do is I would like to enter, just ignore the error table. I would like to enter this and have just boundary IDs, forget about the finite element degree for a moment, but I want to have this section over here and to make sure that everything is done correctly. So the way that I do this here would be the following: std of string or string. And I think this needs an include file, which is not the standard string file, but it's a string file. So there should be string. So this file over here is what I'm going to be pasting the section that I have that, and then passing it as a string to the pass parameters. Okay. So I don't want to do this with files. I want to do this with something which is encoded in the test so that I know exactly what I'm testing, and I can read this right away on the tests. Okay. So for this to be possible, I will exploit Visual Studio nice features. So I will do str and do that, and then I go to the end, close, and do std and line. And this I need to do for everyone except for the first and the last. Okay. I have no idea why this is removed all of those guys. I think I've had an issue with something. Yeah, probably I didn't need all of this. Yes. Okay. So in this way, I've created a string stream actually, that contains the default parameter that I have over there. And with this string, I can actually parse the parameters, call in str, and this should give me str. And there should be a string operator get set content. I think it's str at the end. So if I do that, yes. So if I build this, it should just create a test linear function that creates an object like this, and it passes the parameters. Oh, it's called, I cannot call this parse parameters. So here, instead of calling it parse parameters, I will call parse string, because parse parameters is already taken. So I'll take this as parse string, which means in the Poisson tester, I'll need to use parse string. So in the meantime, is it clear what I'm trying to do, what I'm trying to achieve? So I would like to make sure that I can just copy paste this several times and test different types of objects in here. Okay. Okay, so this is built at the moment. This will just create this grid and do nothing else, okay, in this particular case. So nothing has changed here, except the fact that the grid that is being created will be the hypercube here, and will be the hypercube with 6 global refinements. If I run this, I think this should actually run, and gtest, it should go and have test linear that creates 4096 strings, 4096 cells, which is exactly the thing that I've asked it for 6 global refinements. Okay, so the idea here is I want to test that everything is working correctly. So let's go to the run class, for example, and take a look at the way the run class actually works. And if you take a look at the way the run class actually works, is it creates a grid, set up system, assemble system, and solve. So once it created the grid, you want to call setup system, assemble system, solve. I'm not interested in the error table for the moment, but what I am interested into is not the output results, not the refined grid. What I'm interested into at the moment is to make sure that I can control the error between the functions that I think it's the exact function with respect to the function that I actually obtained. Okay, so I take a vector. You could create a copy of this by saying, for example, auto temp, and I take this to be equal to solution. So I'm making a copy of the solution member of this function. And after I created a copy of the solution member of this function, what I would like to do is I would like to call vector tools, interpolate using the dot handler. And I would like to call, so this takes, in the interpolate takes a dot handler, and then it takes a function, which is the Dirichlet boundary conditions in the way that we wrote things before. I don't have an exact function at the moment. And I want to have, after the function, I will need a function vector valued, and then the vector type. And the vector type is going to be TMP. And now After I've done this, if I've constructed the exact solution in this test, I want to make sure the TMP minus equal solution. I've just interpolated TMP with what I expect to be the exact solution. And then I check that TMP L2 norm is close to 0 with an absolute error of 10 to the minus 10. Okay. And now I build and try to see what happens. This should fail, of course, because I'm not set the exact solution yet. Is it clear what I'm trying to do? I want to make sure that some of the tests that I create actually checks segmentation fault. Okay, C-test. All of them passed.
Well, must be 10 to the power minus 10, not plus 10.
Oh, you're right.
Yeah.
You're right. You're right. You're right. You're right. Of course, it's indeed. Of course, it must be smaller than 10 to the 10. Probably, if I used millions of degrees of freedom, this would have failed. But nothing is particular. Yes, I was very curious to understand why. So now, if I run C-test, there's one that fails, and it's actually the Poisson 2D tester test linear. So I go to the G-test filter equal, and then I call Poisson 2D tester linear. I want to see what's the output of this. If you run this, it will tell you the difference between TMP L2 norm and 0 is 47, which exceeds 10 to the minus 10. And now we start changing this in such a way that everything is correct. So for example, let's take Dirichlet boundary condition expression to be a function which is constant, equal to x. Dirichlet boundary ID is equal to 0. Finite element degree 1. Forcing term expression 0. So I only have 0 boundary conditions. I have grid generator arguments. I set this equal to false. So this is the hypercube with 0 boundary conditions only, with 0 Dirichlet condition array. And I'm saying that the Neumann boundary conditions is nothing for the moment, and the Neumann boundary IDs is nothing for the moment. Number of global refinement, we don't need this many, we only need 4, and number of refinement cycles 1. Output file name is Poisson, and problem constants it's pi. Okay. Now, if I run this, if I build this again and I run this again, what I should see is that the exact solution should be x. I should give I should have a file that is called Poisson.btu_1 on the output which is created when I create this. So this is G-test again, test linear, and now it's passing. And if I open the Poisson 0 VTU output, this is going to be a very boring solution, and it's a linear function, which is exactly what I wanted to have. Okay. Now, this gives you a way to check that what you change in the code doesn't break what you already did. And you have to make sure, one thing that I suggest to people all the time, make sure that you add as many of these tests as you can possibly think. And make sure that you run these tests every time you make a commit or you change something in your code. And this is exactly the idea behind the DL2 library test suites. So if you look at the test suite of the DL2 library, that's about 3,000 tests. And they are run every time you make a commit to the library. And of course, they test all aspects of the library. So maybe you changed just the documentation, so nothing has changed really, but all the tests run anyway. But better be safe than sorry. And I've learned this the hard way a lot of times. So you make a very small change that you think it's not going to do anything different with respect to what you expect, and all of a sudden everything breaks. If you have a lot of tests, this will tell you exactly, it will tell you in advance, very early in the development stage, when this is going to happen. So let's try to do the same thing for a quadratic function. Okay, so for example, if I have the Dirichlet boundary conditions, this is a quadratic instead of that. And I have now set the Dirichlet boundary condition expression to be x to the power 2. Okay, and in order for this to work, the finite element degree has to be equal to 2. I set 0 for term expressions at the moment. And now what I expect is that this should be a parabola. And the reason why it's a parabola is because the shortest path to go from one side to the other of the domain is still going to be a flat line. So there's no forcing term, but I'm imposing x to the power 2 on the boundary. And I can actually get this exact solution using quadratic functions. So I'm expecting this to go exactly in the same way as before. And now here, let me take this as the quadratic functions instead of what that was. And if you compile this, this is just a quadratic function on the Dirichlet boundary, of course. And now I can also use this to test Neumann boundary conditions. Because as we saw before, the Neumann boundary condition that we had obtained before was obtained with a typical type of the same type of things that we had here, but with a little catch. And the little catch was, this is test quadratic and see whether this works. Oh, well, it doesn't. And it doesn't.
You need to change the forcing term because otherwise it's not the exact solution. I mean, it's still parabola, but it's not the same parabola.
Why not? Wait a second. Let's see what we expect this, because this should now be, if I run this, I should have had a quadratic something. Output file name called quadratic. This might say to us that I have not implemented the finite element degree yet. Sorry, FE degree, let me see. FE degree is equal to 1. Okay, by default. And if I set FE degree equal to 1, you're right. Sorry, you're right.
The solution is not
The
exact. Yeah, that's the
yes,
point.
the solution is not exact unless you prove that. So this should be minus 2.
Minus 2. Because minus Laplacian.
Minus 2. You're right. Minus Laplacian. You're right. Not the Dirichlet boundary. Sorry. This is 0. This forcing term expression minus 2. You're absolutely right. Sorry. This was exactly what I would expect. Let's see. Okay, and now test quadratic works. Okay, and now you have the quadratic function which is over here, and one can play, and one can test mixed BC, and the mixed boundary condition would be, for example, in this particular case, x to the power 2 is a function that has 0 Neumann boundary conditions in 0. So one could choose as the true here. And I would expect, for example, by setting Dirichlet boundary ADs to be 1, 2, 3. So I set Dirichlet boundary ADs everywhere, except on Neumann boundary ADs in which I set 0. And in the 0 boundary AD, I set Neumann boundary conditions equal to 0. This should be equivalent to what we had before, because I'm setting x squared as a solution, and the derivative of x squared in 0 is equal to 0. If I look at the size on the left-hand side, okay? And this is mixed boundary conditions test number 1, for example. And as you see, it's very simple to check these things. So you just add, copy, paste, add one test, copy, paste, add one test. And now you have 3, 4 tests that actually check that what you're doing is correct. And the next step is to change the next passage that we had before and figure out whether we get the correct things as well. So this will be much more complicated to, I mean, once you have, okay, now this is exactly correct. So we had exactly what we expected from this type of solutions. And now we change the way they implement the boundary conditions. We use affine constraints, for example, or we add local refinement strategies. If we add local refinement strategies, what's going to happen is that you have to make sure that everything still works correctly. You still have exact solutions if you have finite element degree equal to 2 and second order polynomials. You're not sure whether you're doing the hanging node constraints correctly. Well, we will test this once you have done that simply by copy pasting this and having a different type of test afterwards. Okay? And as you see, if you now run C-test, this is going to check all of the things that we just did with the Poisson 2D linear, quadratic, mixed boundary conditions. And you can be sure whether you did the correct things by looking at the fact that all of these tests have passed. Okay, so let's go forward and let's change what needs to be changed in order to have Neumann, in order to have affine constraints in the actual implementation. So in order to have here, instead of that, I copy linear algebra affine constraints, and I add to this class here, after the triangulation, the defender and the sparsity, after the triangulation and the dot handler, I add a class which is called AffineConstraints on doubles constraints. And if you want to understand how to use this, my suggestion is to go to step 6 of the LII and search for affine constraints. Okay? This will tell you all you need to know about the affine constraints. And the affine constraints class that is used in this guy is called constraints. I'm using the same names exactly for the same reasons. So now I'm searching for the words constraints, and I'll just copy paste what's written here whenever this is used. Okay, so for example, constraints clear DOF tools make hanging node constraints, which passes the DOF handler constraints after you have initialized the DOF handler. So here, what we do is we go to the Poisson.cc, search for distribute DOFs, and as soon as you've distributed the DOFs, you clear the constraints and you make hanging node constraints. Okay, so this will take the DOF handler, compute all the hanging node constraints, and add them into a matrix which is called, well, into an affine constraints object, which contains both the non-uniform degrees of freedom and the uniform degrees of freedom. And sorry, both the hanging node constraints and the Dirichlet conditions on the left. And then you see the constraints also appear in the vector tools interpolate boundary values. And now we do the same thing that we did before. So we do for const auto and ID into Dirichlet IDs. We do that with ID and with Dirichlet boundary conditions. And we pass the constraints object. So now in the constraints, we have hanging nodes and boundary conditions. And now after this is finished, it actually closes the constraint. So here, we don't need anything else anymore. With these 3 lines, we have made the constraints aware of the fact that there may be hanging nodes. And we have made the constraints aware of the fact that there may be different types of boundary conditions for every type of Dirichlet boundary conditions. Questions so far? So these lines over here treat boundary conditions and hanging node constraints for you in a uniform way. Okay. Now, here the dynamic sparsity patterns takes DOF handler dynamic sparsity patterns, which is this guy here. And there's an additional argument that you can pass, which is the constraints, and an additional argument, which is keep constraint offs, which is usually set to false, and we are going to do the same. So now I have modified 1, 2, 3, 4, 5 lines. And let's see where this actually happens again. And now in the assemble system, at the end of the loop, instead of doing this by hand, what we are going to do is we are going to have the constraints do that for us. So constraints distribute local to global. And this will take cell matrix, cell right hand side, local of indices, system matrix, system right hand side, which is exactly what we need here. So basically, this is using all the informations that are used in these 4 lines, these 10 lines in one single function call. And at the same time, it's taking into account of all the constraints. So I remove that. And when I got here, I've already done the boundary conditions, so I can eliminate this safely. The main advantage of using it in this way is that this can also be used in parallel. So if you have thousands of processors, this will work also in parallel, provided that you distribute the degrees of freedom and the constraints correctly at the beginning. So you make sure that the constraints know who to communicate to what and where to communicate from. Okay. So once we have solved the problem, if you look at the next time where the constraints happens, is when you need to distribute the constraints that you just computed to the actual solution. And this is after you have solved the problem. And here is exactly where we're going to add that. So as soon as you have solved the problem, you want to make sure that the constraints have the correct value. And now, if this is correct, everything should work exactly as before. Nothing has changed except the way that we implement the boundary conditions. And so what I want to make sure is that now, when I run the tests, and I will run the tests with the same tests that I had before, the only thing that has changed is the way that I implement the boundary conditions, and I want to verify that everything works correctly in this particular manner. Okay. This seems to have compiled. So I should be able to do the same C-test. And as you see, everything is going exactly as before. So I don't even need to run this again because I get exactly the same result as before. With the difference that this is a little bit faster because this is done locally at the level of the passing from the local to the global matrix. So you don't have to access the global matrix afterwards. So it's much more efficient with respect to what's done before, because you have to do the sum anyway. And if you are summing into a constraint entry, you just don't do the sum. So you're saving a lot of time instead of doing it first and then removing what you did before. Okay. Okay, so I wanted to check just a couple of things. Just one additional part that I want to provide as a test. And I can do this before we implement the last part in the tester. And I want to make sure, for example, with the linear test, simple linear test, I add linear, test linear here with hanging nodes. And the way that I do this is right after I've passed the strings and I have made the grid, what I will do is I will take a look, I will take a loop over the grid that I created. And if the distance of the center from the origin is smaller than 5, say, or smaller than 0.5 square, 0.25. So, well, let me do this first. So I loop over all cells, const auto cell triangulation active cell iterators. If cell center square is smaller equal than 0.25, that means that this is in between the radius of square 0.5, then what I do is I call cell set refine flag. Cell set refine flag. And I do this twice. For assign int I equals 0, I smaller than 2, plus I set a refine flag, and I do triangulation, refine, execute, coarsening, and refinement. This call reads the refine flag. You should have seen this already in the step 1 that we had before. And it does so twice if you are closer to the center, if you are in the square, in the circle, which is closer to the center. So here, instead of doing 4 global refinement, well, the 4 global refinement is okay. This will have some hanging nodes, and then I do everything else. And when I actually output the solution was linear, lean with hanging. And I actually output the solution here as well. So this is the output results on cycle 0. Okay, so if I now build and try to run this test, I should still get 0 as an error because the solution at the end should be still linear solution. So the interpolation between the two should be different, should be exactly as it was. And if it doesn't happen, then there is something strange or something wrong in the test. And it's in fact worked. So if I now open the linear with hanging node 0 BTU, and if I plot it, you shouldn't see any difference, except now if I take the surface with edges, this is more refined on the bottom part. Okay. So to summarize, what we have done here is we have taken the Poisson problem that we had at the beginning. We added a parse string argument that allows us to take all of these tests and prepare all of these tests. And then what we did was to add Neumann boundary conditions. So we implemented the Neumann boundary conditions in the assemble system by adding a similar object with respect to what was done on the cells, but this works on the faces. So it needs a phase quadrature formula, which is a Q-Gauss quadrature formula of dimensions d-1 because it works on faces. And this phase for quadrature formulas is initialized with the same finite element space that we had before. This FE phase values is initialized with the same finite elements that we used here with the phase quadrature formulas, and we ask to update values, quadrature points, and Jacobians times the weights. These are required because we need to integrate Gn times V, and Gn needs to know the position of the quadrature points in order to work properly. And in order to use this, what we do at the end of the loop where we assemble the right-hand side with the forcing term, what we do is we check if we are at the boundary. If we are at the boundary, we loop over all cells, and I'm hopefully this should work, but I don't think it will. Let me check whether this. Oh, I think I've done something. Yeah, so if I uncomment that, I have to. I think this is what we wanted to do. I'm not sure whether this actually works. If it does, I'll remove this and I'll just let you use self-facing indices. It should. I don't remember if this was introduced in 9.3. No. Sorry. It did not complain on this, so this is correct. No, it's not. So we have to go back to what we had before. So phase indices was introduced in 9.3. Sorry for that. So you can use geometry for phases per cell before that. Okay, so here we check whether the cell is at the boundary, and if it's at the boundary, we loop over all faces. And when you have a face which is with the boundary AD of the Neumann boundary ADs, we initialize the FE phase values. This actually computes the values of the quadrature points, the Jacobians, the mappings, and everything that is required for these computations. And then we assemble the Neumann boundary conditions on the right. Okay. After we had done this, we replaced all the occurrences of the interpolate boundary values and apply boundary values with the constraints, and the constraints distribute local to global. This is what's written here. So we did almost everything. This allowed us to have a test, for example, in which we have also local hanging nodes, like in this case. And we didn't finish the last part, which is local pro-refinement and the different types of preconditioners, but this, I'll leave this to you as an exercise. And if you don't manage to finish everything by next week, don't worry. This is going to be the base for the exercise that we do on next Thursday. So let me stop streaming.